lots of different kinds of compounds can go into the combustion category. Metals, nonmetals, compounds, elements, lots of things fit into that flammability. However, the reactions that we look at most commonly in this domain are ones that involve hydrocarbons. That is, compounds that have hydrogen and carbon as their primary molecular structure, and when they burn, will form oxides of carbon and hydrogen that we know better as carbon dioxide and water, usually in the form of water vapor. And so to that end, we see that kind of thing often. The reaction on the board here is the reaction of octane, which is the primary component in gasoline, reacting with oxygen, and we can see that all of the carbon gets turned into carbon dioxide, all of the hydrogen gets turned into water. So when we have combustion reactions of this type, that's our primary set of products. Now, if we react with metals or nonmetals, it's a little bit different. We end up getting metallic oxides or non-metallic oxides as a result. But for hydrocarbons, this is the primary pattern. So in these three pictures, we have examples of well, all of these. In the first photo here, we have what looks to be quite possibly, most likely, sulfur reacting in oxygen, giving us this blue flame to give us a sulfur oxide product, sulfur dioxide. In the second reaction here, we've got magnesium metal. This is a reaction that I believe you did in lab last week. Magnesium metal reacting with oxygen to make magnesium oxide. And then the last one here, this is the common Bunsen burner reaction. We've got the hydrocarbon methane, natural gas, reacting with oxygen to make carbon dioxide and water. So all three of these are technically considered combustion reactions. Again, this one here is probably the most common of the group because it is a hydrocarbon burning, it's a fuel burning. But these other two examples are also examples of types of combustion reactions. So we now have a complete picture. 5 different types of chemical reactions: combination, decomposition, single replacement, double replacement, and combustion. Based upon those key characteristics, we should be able to classify any reaction into one of those 5 categories. And that's what this question is asking us to do. So we have decomposition, which we're going to label as D, combination, C, single displacement or single replacement, both the same, we're going to SD, double displacement, DD. So with those 4 abbreviations, let's classify these 4 different reactions. In number one, I see that I have a couple of reactants turning into a single product. Anytime I see a single product, my immediate reaction should be, this is a combination reaction. If I only have one product, then all of the things that were reactants must have combined to make that one product. This is a combination reaction. In number 2, what I should recognize is that I have common components on each side of the reaction. And all that has happened is that those common components have rearranged themselves. When you see that, you should understand that's a replacement reaction or a displacement reaction. So I'm between SD and DD. Which one is it? Well, I have to evaluate what is on each side of the equation. I have 2 compounds on this side of the equation. I have 2 compounds on this side of the equation. This is double displacement, double replacement. Where does the double come from? The fact that I have 2 compounds on each side. In number 3, I've got nickel 2 sulfite turning into nickel 2 oxide and sulfur dioxide. Again, the real key here, single reactant breaking apart into multiple products. That is by definition a decomposition. In the last one here, I should again be able to recognize that there are common components on each side of the equation. I've got calcium on each side, I've got lead on each side, I've got chloride on each side. The only difference is that the chloride was with the lead and now it's with the calcium. So I know that this is a displacement reaction. The 2 elements are displacing each other. It's a matter of how many reactants are compounds. And I can see that I only have the 1 compound here and the 1 compound here. Calcium and lead are elements on each side of the reaction. This is a single displacement. An element is turning into a compound is breaking apart and giving us a new element. Only 1 compound on each side. Any questions about this particular example? All right, let's move on then. All right, in this reaction, I have something in solution. That something in solution is copper 2 sulfate, CuSO4 aqueous, and I've got an iron nail Now, in this reaction, I want you to focus on what's going on inside of the solution. Don't look at the nail that's sticking out in the air. Look at the nail inside the solution. Look at the solution itself. I can notice here that I've got copper sticking to that nail. That's that red solid that is stuck in and around that nail. I also should notice the blue color that was the copper sulfate solution isn't there anymore. What's left over and what's actually taken over in that case is iron 2 sulfate, FeSO4 aqueous. So here's my before, here's my after. Clearly a chemical reaction has taken place. What kind of chemical reaction is it? Okay, Rachel is saying that it is single replacement. I heard a decomposition here in the room. Well, it's not a decomposition. I would need to have one reactant, and I don't. I have two. What I need to look for are those commonalities again. I have sulfate here and here. I have copper here and here. I've got iron here and here. So from that, I can see that I've got a replacement reaction here. Because all that's happened is I've got the same components, copper, sulfate, and iron. They've just rearranged themselves. Now, is it single or is it double? Well, how many compounds do I have on each side? I've got copper sulfate, that's a compound. I've got iron, that's just an element. I've got copper, which is just an element here. I've got iron sulfate, which is a compound. One compound on each side. This is single replacement or single displacement, however you want to frame it. Other questions about this example? All right, try this one for yourselves. Put your answer into the chat. What kind of reaction is this? Got a couple of answers of combination in here, and that would be correct. I've got one product, one unique product here, ammonia, NH3. All of these molecules shown are all the same. They're all NH3s. They all started from nitrogen and hydrogen. So I had multiple reactants turning into a single product. That's combination. All right, let's look at this one. Might be a little bit tougher to see interpreting the picture. I've got copper here. I've got silver and nitrate. And on the flip side, I now have silver, copper ions, and nitrate ions. All right. So again, automatically, your brain should be going to, I've got commonalities. I've got nitrate on both sides. I've got copper on both sides. I've got silver on both sides. So this is a replacement reaction. It is a single replacement reaction because, again, one of our reacting components on each side is an element, not both of them. Both of them have to be compounds in order to be double replacement. All right, let's look at one more. Early consensus says it's decomposition. And the early consensus in this case would be correct. This is actually the compound iron 3 oxide. And we can see that it is split into oxygen gas and iron metal. So one ionic compound has split apart into multiple elements. That's decomposition. All right, any questions about some of these picture panel examples? In these particular view ones, it can be a little bit difficult sometimes. You have to really get into what it is actually being shown. Okay. One last look. No picture panels here, just straight up. 10 equations, classify them. Into which group do they belong? Combination, single replacement, double replacement, decomposition, combustion. Let's go 5 minutes. Talk it out with each other. Put your answers into the chat if you're offline. I'll be around to talk to those of you that are here. All right, so it was asked here in the room. If you don't have all of them done yet, that's okay. Just go ahead and get the answers while we kind of talk through them. It was asked here in the room, how do I know when a combustion reaction is occurring? And notice that none of these are combustion reactions. Combustion reactions, you have to have something reacting with oxygen. So combustion is substance plus oxygen yields products. If you don't have that particular formula, it's not going to be a combustion reaction. So in none of these cases do we have a combustion reaction. Any questions about any of these 10? All right, number 8. All right, so in number 8, this is a double replacement reaction. How do we know it as a double replacement reaction? Again, it comes down to, are there common threads on both sides? So in a combination reaction, for example, I can't pick out anything in the products that was there in the reactants other than just elements. Yes, there is calcium, carbon, and oxygen on both sides of the equation, but there's no CO3s in the reactants. There's no O3s. The only thing that's really common is there's a carbon and a calcium on both sides. I really can't even pick that much out as being common. In decomposition reactions, there really are no common threads there either. Yes, I can see that there is mercury on both sides of number 7, but the oxygen is completely different in the reactant versus the product. But in replacement reactions, I can see that there are common threads. Everything that was present in the reactants is present in the products as well in its ionic form. And that's the thing that you really have to kind of remember, is that replacement reactions happen with ionic compounds. And those ionic compounds tend to have similar charges before and after. So I look and see, okay, I've got sodium on each side. I got sulfur on each side. I've got hydrogen on each side. I've got chlorine on each side. All that is changed as we have proceeded is that the elements that were together in the reactants are together with different parts in the products. In particular, we can see that the sodium and the hydrogen have switched places here. Sodium is now with chlorine, hydrogen is now with sulfur. They haven't changed any of their identities. If I look at it from the standpoint of charge, sodium is +1, sulfur is -2, hydrogen is +1, chlorine is -1 in these ionic compounds. And sure enough, we've got the exact same charges on the other side of the equation. Everything's the same. The only thing that's not the same is what they're associated with. The sodium was with the sulfur, it's now with the chlorine. The hydrogen was with the chloride, now it's with the sulfide. So that on its own puts us into the replacement area. The fact that we call it double replacement has to do with the fact that both of the compounds on each side are compounds. Both of the substances are compounds. If one of those substances was an element, like in the case of number 4, chlorine and iodine are both elements. They're molecular elements, but they are elements nonetheless. That's what makes it single replacement. In double replacement, I have to have two compounds on each side of the equation. All right. Any other questions on this page? Okay, I originally was going to start chapter 6 in this spot. However, given that I have exactly 6 minutes to go through more than 6 minutes of material, we'll finish up today by talking about word equations. Now, word equations are the subject of the last proficiency that you have to do in this class. It's called not balancing equations, but writing equations. Word equations put together the concepts of the two previous proficiencies, nomenclature and equation balancing. So to do these kinds of problems, I need to do two things simultaneously correctly. First, I have to find the correct formulas for the compounds in the equation. And if that wasn't hard enough, I then have to make those compounds into a balanced chemical equation. I've got to do all of that balancing, atom economy kind of stuff. So we've only got about 5 minutes. Let's take a look at this first equation. And so I am going to hop from the PowerPoint here over to the whiteboard to give us a little bit more space. Okay. It might have been earlier in the presentation. I think in my original slides, it was like slide number 25 or something like that. And I moved it to the end because it was more appropriate there. But it should be there. It is in my notes version earlier. Okay, so we've got to go through the first part of this. And once we've established the nomenclature and getting the correct formulas here, then we can go about balancing it. So potassium chlorate, potassium, element K, chlorate, I'm dealing with an ionic compound here, so I need to know charges. Potassium is in the alkali metals. It is a +1 charge. Chlorate ion, ClO3 with a -1 charge. So I've got potassium chlorate, +1, -1. Charges match, so the compound itself exists in a 1-to-1 ratio. The formula for potassium chlorate, KClO3. Now I've got to do the rest. Potassium chloride. Again, I should recognize I've got a metal and a non-metal here. This is an ionic compound. I'm going to need charges. Potassium, we established previously, +1 charge. Chloride ion, Cl. I look at the chloride, it's in the halogens, -1 charge. Once again, I've got like charges. So the formula is 1-to-1 KCl. Oxygen is an element. O is its symbol. However, we have to recognize that oxygen is one of those molecular elements. And as a molecular element, it exists as O2. If you need refreshing, the molecular elements are hydrogen and the 6 elements in the top right corner of the periodic table that form a 7 shape, starting with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. 7 elements in total exhibit this behavior. Oxygen is one of them. So if I see oxygen or fluorine or bromine as a compound or as a product, as anything in a chemical reaction, I have to understand it's going to show up as the diatomic molecule, not just the atom. Those are the only 7 that do that. Everyone else, if it says manganese, you can just put in Mn in that spot. But now we go to balance. I have 1 potassium, 1 chlorine, 3 oxygens. 1 potassium, 1 chlorine, 2 oxygens. Remember our rule of thumb. If we get to a spot where we have an odd number needing to be balanced by an even number, the way to get around that is to double everything else. So I'm going to double the potassium chlorate. I'm going to double the KCl. That gives me 2 potassiums, 2 chlorines, 6 oxygens, 2 potassiums, 2 chlorines. Now to make 6 oxygens, I would need 3 oxygen molecules to get it to balance all the way. So that's a little bit of a taste of what that last proficiency is all about. Now, I would not recommend attempting this proficiency until you've passed nomenclature and you've passed equation balancing. And right now, there is a very, very, very select few of you that have passed one of those, let alone both of those. So I wouldn't go too much further with that, but understand that that is on the horizon. On Friday, we will pick up and talk about Chapter 6. Chapter 6 is a very short chapter for us. We're only going to be covering 2 sections out of it, and we'll be doing those in relatively light detail. So we'll probably only do it Friday and then the following Wednesday. But that's all I have for you now. Have a good afternoon.